Welcome to Spaceverse, your portal to cosmic adventures. Supernovas in the early universe just hit different. They weren't just spectacular, they were wild, raw, and unimaginably powerful. Back then, the cosmos was young, chaotic, and filled with stars unlike anything we commonly see today. These were not your average suns. They were stellar monsters, behemoths burning hotter, living faster, and dying harder than most stars do now. We're talking about giants 20 times the mass of the sun, living on the edge of instability. When they died, they didn't just vanish quietly. They tore themselves apart in explosions so intense, so bright that they could light up the early universe. And now, thanks to the incredible infrared eyes of the James Webb Space Telescope, astronomers have captured the light from one of these ancient cosmic deaths, one of the most distant, and therefore earliest, supernovas ever discovered. This explosion, now named AT-2023 ADSV, didn't just happen long ago. It happened in a universe that was just starting to take shape, about 2 billion years after the Big Bang. Imagine that, the universe was only a fraction of its current age. Galaxies were still forming, heavy elements were rare, and stars were blazing their short but epic lives across the dark canvas of space. And then one of those stars, massive, unstable, magnificent, collapsed under its own gravity and detonated in a blast that echoed across billions of light years. This is more than just a discovery. It's a window into the very first chapters of cosmic history, a glimpse at how the earliest stars lived, died, and forever changed the universe. This supernova, detected as part of the JWST Advanced Deep Extragalactic Survey, or JADES program, could help scientists add even more detail to the growing cosmic picture of stellar life and death. The event has been designated AT-2023 ADSV, and it erupted approximately 11.4 billion years ago in a massive galaxy that existed when the universe was still young and wild. But what really makes this discovery exciting is that this stellar explosion seems to be somewhat different from the supernovas we're used to seeing in our relatively modern universe. It wasn't just far away. It was extreme. The explosion was so energetic, so violent, that scientists are questioning whether the very nature of supernova explosions might have been different during the early stages of the cosmos. The first stars to ever form were a different breed. According to David Coulter, a member of the JADES team and researcher at the Space Telescope Science Institute, the first stars were considerably different than the stars today. They were massive, they were hot, and they had truly gargantuan explosions. Speaking at the 245th meeting of the American Astronomical Society, he went on to say, "We don't know how many supernovas the JWST will find, but we can start to push to the beginning of these first stars and hope to see their explosions." It's a story of stellar life, death, and rebirth. The early universe was chemically much simpler compared to the modern cosmos. Back then, hydrogen and helium dominated the scene, the two lightest and most basic elements. Heavier elements, what astronomers call metals, even though this includes things like carbon and oxygen, were barely present. The first generation of stars, known as population 3 stars, formed from these nearly pristine conditions. Born in overdense pockets of this elemental soup, these stars started fusing hydrogen and helium into heavier elements. They were enormous, short-lived, and burned intensely hot. And when they reached the end of their lives, something extraordinary happened. For stars more than 8 times the mass of the Sun, the nuclear fusion in their cores would eventually cease. Gravity, now unopposed, would crush the core down into a neutron star or black hole. The outer layers, rich in newly formed metals, would be expelled in a catastrophic explosion, a supernova. These early supernovas acted as a kind of cosmic enrichment program, spreading heavy elements across the galaxies. This enrichment allowed a second generation of stars, population 2, to form with more metallicity than their predecessors. Eventually, this process led to a third generation, population 1 stars, the metal-rich stars like our own Sun. This cosmic cycle, birth, death, enrichment, and rebirth, repeated over billions of years. But while this pattern might make it seem like a simple loop, the first round of supernovas was anything but ordinary. Scientists believe that because these first stars were metal poor, they lived shorter lives and exploded with greater violence. Their supernova explosions would have been brighter, more energetic, and possibly more chaotic than anything we typically observe today. And because they were so bright, they are exactly the kind of phenomena that the James Webb Space Telescope is built to detect. That's where the JADE survey comes in. Focused on the birth and evolution of early galaxies, this program has already identified over 80 ancient supernovas, each one a relic of a time when the universe was still finding its rhythm. Studying distant supernova explosions is the only way to explore the individual stars that populate these early galaxies, said Krista DeCourcy, a team member from the University of Arizona in Tucson. The sheer number of detections plus the great distances to these supernovas are the two most exciting outcomes from our survey. And among these many discoveries, a T2023 ADSV stands out not just because of its age or location, but because of its unique chemical makeup. This supernova is so far away and therefore so far back in time that when the light was first coming to us, the universe was less than 2 billion years old, Coulter explained. That means that this light had been traveling 6 billion years before the sun ever formed. The environment in which this supernova occurred was considerably different from our solar neighborhood today. It was a raw, metal-poor environment, a hallmark of early cosmic conditions. Yet, there's a twist. While AT2023 ADSV occurred in such a pristine setting, it shares an odd resemblance to some local supernovas that occurred in similarly untouched environments. It appears to be a close cousin to local supernovas observed in similarly pristine environments, Coulter noted. However, the resemblance stops there. 2023 ADSV appears to have been once a particularly massive star, perhaps up to 20 times the mass of our Sun. Stars of such enormous size are extremely rare in today's universe. In fact, they're almost never found in our stellar backyard. But in the early universe, giants like these were far more common. And this particular star didn't just die, it died dramatically. The explosion released about twice the energy of a typical supernova caused by a massive nearby star. It was, in every sense, a cosmic overachiever in destruction. According to Takashi Maria, a theorist with the National Astronomical Observatory of Japan, the high explosion energy of 2023 ADSV could indicate that the properties of supernova explosions might have been different in the early universe, but we need more observations to confirm this idea. Fortunately, help is on the way. In 2026, NASA is set to launch its next major space telescope, the Nancy Grace Roman Space Telescope. Roman will offer a wide field of view, making it ideal for spotting distant and ancient supernovas in the early universe. While JWST has unparalleled resolution and sensitivity, it's designed for targeted observations. Roman, on the other hand, is the cosmic scout, the wide-eyed explorer that will locate thousands of candidates for JWST to study up close. The synergy between these two telescopes promises a new era of cosmic discovery. With Roman casting its net across the vastness of space and JWST zooming in with precision, astronomers will be able to paint a far more complete picture of how the universe evolved from a hydrogen-helium soup into a richly structured cosmos full of planets, life, and galaxies. The research behind AT2023 ADSV was presented at the 245th meeting of the American Astronomical Society, and a preprint of the team's findings is already available on the Arxiv repository, a sign of how eager scientists are to share and build on this landmark observation. So what does this all mean for us? It means that thanks to JWST, we're now able to witness the universe in its youth, to watch the earliest stars live out their lives and explode in brilliant death. It means we're beginning to unravel how the very first supernovas set the stage for everything that followed. And it means the deeper we look into the cosmos, the more we learn about ourselves. Because in a very real way, the heavy elements forged in explosions like AT2023 ADSV are what made planets, oceans, and even human life possible. In the death of ancient stars, we find the seeds of life. And this is only the beginning. And that's it. Thanks for joining us on this journey back to the dawn of the universe. From stellar giants to ancient supernovas, the cosmos is still telling its story, and with James Webb watching, we're finally learning to read the light. This is Spaceverse, where stars die, galaxies are born, and the universe comes alive. Until next time, keep looking up.